Okay, welcome to our Zane State Physics 2010 Chapter 7 video, our series of videos on linear momentum. So momentum is another of these physics terms that you're probably familiar with. It's often used in everyday conversation. So all we need to do is to formally define it so that you can understand specifically what it means in a physics context. So momentum is a vector quantity. We use the letter P to represent momentum. I'm not really sure why they use the letter P for momentum. My guess would be M is obviously already taken. M is mass. Maybe N is used for something else as well. O is too close to 0, so maybe they just went down the alphabet and thought, well, if we can't use M or N or O, let's go with P. But that's just a guess on my part. I've had some students jokingly, to help them remember that P is momentum, refer to it as po-mentum, and I thought that was kind of funny. So I've remembered that and still use it to this day, po-mentum, to help you remember that P is momentum. So it's equal to mass times velocity. So if you have more mass, you have more momentum. If you have more velocity, you have more momentum. So I've included this image here of a bowling ball hitting the bowling ball pins. If you want to increase your chances of knocking down all the pins, you want to give your ball more momentum. So using a heavier bowling ball will help you out, and rolling it faster will also help you out. Those two things increase your momentum. And if we look at it in this different way, if we take our mass times velocity and we change it in some amount of time, velocity, the change in velocity over time is acceleration, and m times a, according to Newton's second law, is force. So we can say that a change in momentum over time, mv over t, is equal to ma, which is equal to force. So the sum of forces acting on an object can be described as a change in momentum over a change in time. So when this bowling ball strikes the pins, its momentum is transferred to the pins. It delivers a force to those pins and knocks them over. Let's look at an example problem here where we have a tennis ball being served. It's leaving the racket with an initial speed of 55 meters per second. So we're going to assume that this girl has tossed the ball up into the air, and right as the ball is at its peak of trajectory, right where its velocity is 0, that's when she hits it. So we can say that the initial velocity is 0 and the final velocity is 55 meters per second. So the change in velocity, we went from 0 to 55. So that's 55 meters per second change. The ball has a mass of 0.06 kilograms, and the amount of time in which the two are in contact with each other is a very small amount of time, 4 times 10 to the negative third second. We want to know what is the force on that ball. So as we said in a previous slide, the sum of forces equals the change in momentum over the change in time. And the change in momentum, or momentum, is mv over t. So our mass was 0.06060 kilograms. And the change in velocity we already determined was 55 meters per second. and the amount of time that they spend in contact with each other is 0.004. Let me double check how that was presented with significant figures. Yeah, just the one significant figure, 4 times 10 to the negative third. So it's 0.004 seconds. And so when we calculate this, we should get that the sum of force on the tennis ball is approximately, rounding just to one significant figure, 800 newtons. 800 newtons of force is delivered to that tennis ball. So momentum is much like energy. It is conserved. So this is useful when investigating issues where we have two or more objects colliding. We're going to just specifically look at two objects colliding that share a line of motion. So if we have this line here, they're each moving along the same line, and in this case, they're moving towards each other. So object A is moving to the right, object B is moving to the left. They're going to collide, and so momentum is going to be transferred over a short period of time, and so essentially they're going to cause forces on each other. And the result of that, depending on the mass and relative masses and velocities, they could both go off in opposite directions from where they started. So A was initially moving to the right. It will bounce off of object B and go back to the left. Object B collides, and it was initially going to the left and now will go to the right. That's one potential outcome here. Imagine, though, that A has much more momentum. Let's say that this is like a bowling ball and B is a ping pong ball. It's unlikely that object B, in that case, would have enough mass and therefore enough momentum to cause A to bounce back to the left. So it's possible that after this collision, depending on what their relative masses are, that both objects end up going to the right. So that's something we'll have to investigate. But we can do that by knowing that the total amount of momentum within the system before and after the collision is equal to each other. So if we take the momentum of object A, which is m sub A times v sub A, and the momentum of object B, which is m sub B times v sub B, then it will be equal to the momentums after the collision. So we show that m sub A, the mass doesn't change, so m sub A here is the same as m sub A here, but the velocity will likely change. And so here we have v prime. When we use that little like apostrophe symbol there, we call that v prime sub A, and that's used to show that it is after the collision or the event being studied. And then we have m sub b. Again, the mass doesn't change during the collision, but the velocity will. And so we have v prime. And again, that's denoting that it's after the collision. Okay, let's put this into the context of an example problem. Well, we will hear in just a moment. So in this example here, we had the two objects collide and bounce off of each other. We can also have collisions where after the two objects collide with each other, they actually become one. So it could be a couple train cars, as we see here. When this train car hits into this one, they will actually mechanically link together, and then they will both travel at the same speed. So that's a key to solving problems like this, is knowing that the final velocity We may not know what it is, but we do know that it's the same for the two objects because they're actually linked together. Some other example problems the textbook might use are things like lumps of clay colliding with each other. We have one lump of clay and another, and the one slams into the other, and instead of bouncing off of each other like billiard balls, they actually then, the two of them kind of clump together and become one object with one single final velocity. So let's now look at an example here where we have a 10,000 kilogram railroad car. Mass is 10,000 kilograms. And it's traveling at 24 meters per second. So its velocity is 24 meters per second. It strikes an identical car B. So this also has a mass of 10,000 kilograms. But its velocity is 0. It's stationary. The cars are going to strike. They're going to lock together. What is their common speed afterwards? So v prime. The velocity after the two objects collide. What will it be? Okay, so we've got a little animation to show that they'll collide, they'll stay together, and then they'll have some final velocity. So we know that the momentum is going to be conserved. So m a VA, that's the momentum of car A, plus MB VB, that's the momentum of car B. So before they collide, that's the total momentum, just adding the momentum of each of these cars. And when it's finished, the two masses are going to be combined. They're going to combine into one linked train that has a mass of ma plus mb, and they're going to have the same final velocity. So that's what we want to know, what that final velocity is. So we can solve for v prime and see that that is going to be MAVA times MBVB divided by MA plus MB. So the mass was 10,000 kilograms, and it had a velocity of 24 meters per second. And, over here, this should have been a plus, sorry. And MBVB, MB is also 10,000, but the velocity of car B is 0. So that whole term is just going to become 0. Divided by the combined mass, 10,000 plus 10,000 is 20,000 kilograms. And so when we calculate that out, we see that the final velocity of the combined train is going to be 12, just 12. Well, let's check our significant figures. Yeah, I believe the 24 that is given to us is our limiting factor. Again, this 10,000 value, are these zeros significant or not? It could be argued that they are not, but it's the author's intention actually that they are. So we look to the 24 to limit us to two significant figures, so the velocity is 12 meters per second. And you could have possibly guessed that just by looking at the situation, knowing that they're both of equal mass, and the initial velocity here of A was 24 meters per second. And when the mass doubles, the velocity has to be cut in half in order to keep the momentum conserved. So this is a pretty straightforward example, but it does illustrate the conservation of momentum.